All right, so functional groups. As we move towards functional groups, we need to realize that they are different than hydrocarbons because they're going to have more electronegative atoms. More electronegative atoms just means they're going to be more polar. So hydrocarbons, almost exclusively, we can just kind of generalize and say nonpolar. Nonpolar means they're weakly held together because there's no real attraction from one to the next. We can see this because if we think about H2O, H2O is very common on the planet. It boils at 100 degrees Celsius. Notice for a hydrocarbon to match that strength, because temperature is a good relationship to strength, you can imagine that minerals, rocks, they don't melt for thousands of degrees, but water melts at 0, it boils at 100. Temperature is a great way to recognize strength. And what we see for hydrocarbons is we need to get almost all the way to, say 7, 8 carbons in order to equal the strength of water. That's crazy to think because water only weighs 18. It's hydrogen plus oxygen, so that's 1 plus 1 plus 16. So it only weighs about 18 grams per mole. We'll talk about moles much later in the semester. But just think of the word, or at least the size, 18 grams. Once you get to octane, you're looking at, C8H18 in order to be almost as strong as water in boiling point. In this case, a little bit higher at 124. This would be 8 times 12, plus another 18 times 1, which is the relative sizes of carbon and hydrogen's atomic weights. So you're looking here at over 100 grams and change versus only 18 grams. The major difference is water's polar, and all of these are not. And that's a huge difference of how we make and understand the human body coming up in our next chapter. If we want to be strong, we need to have atoms that are electronegative like oxygen, like nitrogen. And that's what we're going to see coming up in a lot of our functional groups. So what it means to be a functionalized group is we're taking away carbon, maybe even hydrogen, and adding in something that is more electronegative. So in this example here, notice what we have is removing 1 hydrogen. We boil at negative 164. This is cold enough that if your finger was at negative 164, you could slap it on the table and it would shatter like glass. Super cold, frigid. Just by removing a hydrogen that has electronegativity of 2.1, throw on a chlorine that has electronegativity of 3.0, notice we jump all the way up to negative 24, which is still cold. Don't get me wrong there, it's still well below freezing. But it's basically 120 degrees, 140 degrees stronger, warmer in the sense of these frigid temperatures in order to break these molecules apart. If we were to remove 3.0 and add 3.0, doesn't seem like much of a difference, but then we add 2 hydrogens to those that are at 2.1. Now we have significant dipoles between nitrogens and hydrogens in particular, not to mention the small dipole that's between carbon and nitrogen. Really no difference in strength of carbon and chlorine. We jump up another almost 20 degrees. Replace that nitrogen with oxygen at 3.5. Attach it to a hydrogen at 2.1. That's now superpolar as well. And we jump up almost another 70 degrees. So if you want your body to be strong, if you want your drug molecules to get rid of your headache for a long time, we want things that are strong and not things that are weak. So most of what holds the human body together are these carbon, nitrogen, carbon, oxygen kinds of groups. And this is why. They have strength because it takes higher temperatures in order to break them apart. And that's the reality of all of these chapters on exam 3. Recognizing strength, recognizing the glue that holds these molecules together. In our first video over organic chemistry, we talked about 9 million organic compounds and counting. 50,000 each year, 90% of everything. And a good portion of those are hydrocarbons. And the problem with hydrocarbons is they're mostly fuel, they're mostly lubricants for our engines that burn the fuel. The rest of the world, though, the plants, the animals, the medicines that we treat those plants and animals with, those have functionality. those have not just C's and H's, but O's and N's and F's and CL's and BR's and so forth. So in 2 separate videos, we're going to show you that there's 10 functional groups that we cover in Introchem, 5 with a carbonyl. Carbonyl is just C double bond O. So carbonyl, by definition, is C double bond O. So there's 5 that have that group and there's 5 that don't. We're going to talk about the 5 that do in a video, and then we'll talk about the 5 that don't in a separate video. So as we look at the 5 that don't have carbonyls, so there's no carbon double bond oxygens, we see these R versus AR ideas that we saw in one of our early videos. R just stands for random. There's 9 million choices there, so more than you want to count. But that really applies to the alkenes, alkynes, and arenes. The only time that we really need to worry about arenes versus random groups is here. Alcohols have a random group. Phenols specifically have an arene. So any kind of chains with OHs, they could have branches, whatever, those are alcohols. But specifically when you have a hexagon with alternating double bonds and then put on an OH, that's the arene. So having those different from these, very important, because that's the only way to tell them apart. They even have the same last 2 letters, OL, in their names, so be careful there as well. So one of the features that we want to recognize here is organic halides. So they're going to have halogens, so halides, halogens, same thing. So think of fluorine, chlorine, bromine, iodine there. Alcohols like the drinking type, phenols like the chloroseptic throat spray type, ethers like the fire starter, carburetor, starting fluid kinds, a lot of old anesthetics before they went to laughing gas. And the amines, which is a lot of in our body, like dopamine and methamphetamines, those kinds of things, recognized by their nitrogen atoms. So as you look at each group, we'll just talk a little bit about them, recognize a little bit of their naming, not too different than what we've seen before. Organic halides all going to have a halogen. So this is group 17 on the periodic table, Roman numeral 7. They're going to connect to one single bond to carbon and give it a little bit of polarity. Most of these are on the edge of having enough strength to be gases, liquids right around room temperature. So a lot of these are refrigerants. If we make very long chains, we can make them into nonstick coatings like Teflon, which is tetrafluoroethene based. A lot of things like vinyl, whether it's a record or a rain jacket or so forth. But most of these, could be bug killers. These can be dry cleaning fluids. They can be coatings on baking pans and cooking pans and so forth. Not too useful in the body. Actually, they're pretty dangerous for the body because of that carbon-chlorine bond. It can attach to DNA and mutate it and cause cancer and so forth. So a lot of those aerosol cans, not too good to breathe for that reason. As we look at some of their names, just realize that it's following the same rules. Here we have 5 carbons. 5 carbons tells us use the pent prefix. It's all single bonds. So we've used the ane suffix. Location was 2. It could have just as easily been 4 from the wrong side. That's going to be the easiest wrong answer. And then this is iodine, an atom. And notice they changed that to iodo. So chlorine, chloro, bromine, bromo, fluorine, fluoro. But it follows the same kinds of rules as, say, a methyl. It just changes the ending of the name just a little bit. And then it's still based on location, based on the parent length that we look at its name. Won't see too many of those, but there are, I think, 2 or 3 homework questions based on it. Alcohol is a little bit different. Alcohols are going to have OH, and these OH groups going to be common in things like rubbing alcohol, which is isopropyl alcohol or isopropanol. Also in ethanol, so notice in both of these examples here, you're ending in OL, you're ending in OL, or even the word alcohol ends in OL. So that's the easiest way to recognize it from other groups. Just keep in mind, so do phenols. Phenols also end in OL, and they're going to have an arene group, but they also have this OH that's very polar. Drinking alcohol is going to be 100%. That's 200 proof. And then you have various drinks that have lower percentages that are more water-based and less alcohol-based. Anything with high alcohol content is going to be very dry because it's going to kind of use osmosis, use diffusion to get the water out of your mouth to kind of turn into a solution. What makes alcohols so important is they have high solubility in water. So a lot of our drug molecules are going to have alcohols. They're going to have these OHs, and eventually what we're going to see with amines is NHs because they're superpolar, just like water. They're going to interact with water. They're going to be soluble in water. So they're going to be soluble in the bloodstream and in the body. So this ability to hydrogen bond, very important because that's the strongest attraction that molecules can have, and alcohols have it. Not many other groups do. When we name alcohols, we name them based on their OL ending. And when we do this, we have to make sure that we can recognize their formulas. Their formulas are very similar to an alkane. Alkanes have the same formula of CnH2n plus 2. But then they also have the oxygen. Be careful because that's the same formula as an ether that we mentioned earlier because it's edge versus middle. You also have to be aware that there's other groups with oxygens like aldehydes and ketones that are edge versus middle, or acids and esters that are edge versus middle, and what makes them different is the number of hydrogens or the number of oxygens. So for those 6, they can be pretty tricky just because they're different by H's and O's. So pay attention to that. As far as naming goes, we have pent, which is 5 carbons. We have ane because it's all single bonds, and now OL because it's an alcohol. And notice the number is still just a location on the 5 to find the OH group called the alcohol. So as we look at these alcohols, let's think about how to name them. So as we look at these, we think, what is the longest parent? So counting across, I'm going to count from the short side just to keep from having to write over myself. Here we have 4. And from the alcohol, we also have 4. So either way, both of these have 4 carbons. That just means both are going to be bute. Then we realize that they're all single bonds, and that's going to be butane, or butane in our case. The reason we don't say butane is because it's functionalized. It has an alcohol group. So we're going to say butanol. The major difference between these butanols is the location of the alcohol. It's either on the first, it could be on the fourth. That's just the easiest wrong answer. Could be on the second, it could be on the third, in this example on the left, 2 being faster than 3, and then 1 being faster than 4. So this is just a difference in the type of butanol. That alcohol group itself is the OH, so that's the OL. The butane just says 4 carbons, and then 1 again is location. 2 is location. So very similar kinds of naming concepts to what we saw earlier. As we look at phenols, remember that they too end in OL, just like alcohols. These are very much more acidic because of their stability of the group of atoms once they've lost their hydrogen atom. So because they're so acidic, we can't use very much, otherwise it's dangerous. So in chloroseptic throat spray, we only use about 1%. Anything higher than that would give your throat blisters or lesions that would last for weeks just because of their strong acidity. But about 1% is good for using that acidity to kind of dissolve away some of that mucus in your throat and kind of numb it at the same time in order to keep that bacteria from proliferating. Ethers is a group that is very easy to recognize because they typically use the entire word of the group, ether. So what's unique about an ether is the ether name, right? All these groups have the ether name because they represent this ROR kind of group, this R random OR kind of group, and that's pretty common for all ethers. If you have one carbon on both sides, it's going to be dimethyl because methyl means one carbon. If you have a 2 carbon versus 1 carbon ether, you're just naming those groups separately based on the length of the chains on each side. If you have 2 groups that are 2 carbons, again, diethyl. So alphabetical order, somewhat important here, but what's most important is ethers have oxygens in the middle. They're going to lose the polarity that alcohols and phenols have because they don't have that OH that's going to be superpolar compared to their oxygen carbon bonds that are just a little bit polar. Unique to the formula is alcohols. So CnH2n plus 2O is also the alcohol formula, so there is no difference between them other than edge versus middle. Notice they lose their solubility with benzenes, with arenes. So we'll see this in a lot of examples. These C6H5 rings do have high boiling points just because they have lots of atoms. But more importantly, they tend to be insoluble in water because this is a lot of hydrocarbon, this is a lot of hydrocarbon. Those are very oily, and oil and water don't mix. So what little polarity this oxygen introduces is typically not enough when those hydrocarbons get very long, and we'll see that for a lot of different examples. Eventually you can overwhelm your polarity with hydrocarbons and then kind of overrule it. Amines are also the major group for our next chapter because we're going to talk about amino acids and the protein portion of that chapter. But amines very polar because they're nitrogen to hydrogen bonds. Just like alcohol is very polar for their oxygen hydrogen bonds. And really we only have one nitrogen group in this category, and we have one in the category where the carbonyl looks just like it. Lucky for us, the name, just like ether, in this case amine, is part of all the answers. So that's the easiest way to recognize amines, is just recognize a portion of the name that matches exactly that. Amines are the only groups with a nitrogen atom that we have to worry about without carbonyls. The other ones are going to be very similar sounding. Those are amides, only one letter difference, but they're also very similar in spelling, which helps recognize those being nitrogen based and all others not. Another unique idea about amines is that they are bases. Bases are things that can accept hydrogen atoms from acids like carboxylic acids in the other group of 5. Also unique to amines is their fishy, kind of unpleasant smell. This is very common in things like fish that is full of protein. Those amino acids, when they're decaying, when they're dead, or even when they're alive, have that smell of meat. So how do we hide this? Well, we can throw in lemon juice that has citric acid or vinegar that has acetic acid and kind of quench that smell, kind of take away that smell. So if you ever go to buffets with shrimp or with salmon or any kind of fish, a lot of times they have lemons there, and that's to use chemistry to take away some of those amines by smell, by giving them protons, by giving them hydrogen atoms in the form of acid. So not only for flavor, but for smell do they use those kinds of ingredients. And then we get to the other 5, which we'll come back to in a separate video.